The first 3 paragraphs of the introduction explain the meaning of the title, and the entirety of the text since then has been an attempt to explain the meaning of the first 3 paragraphs of the introduction, which I will now quote. Winning arguments is what I aim to show how to do in this text. I will show how this can be done by constructing winning arguments. As just illustrated, the phrase winning arguments has at least 2 important senses. First, winning arguments can be interpreted to refer to an activity, the activity of winning arguments, where argument here is used in the sense of debate. Second, winning arguments can be interpreted as a noun phrase, where argument is used in the sense of a series of statements designed to provide reason to believe some conclusion. In this interpretation of the phrase, winning is an adjective, presumably meaning something like persuasive. Back in the introduction, I gave a series of words from the first 3 paragraphs that needed explanation. Those words were debate, argument, winning, true, reason, believe, persuasive, and statement. We've done some analysis of debate, argument, winning, and combinations thereof, but the rest of these words remain to be analyzed: true, reason, believe, persuasive, and statement. In this section, we shall analyze the word statement. What is a statement? A statement is a kind of sentence or sequence of sentences. Here are some dictionary definitions of statement that I looked up on Google. A definite or clear expression of something in speech or writing. An official account of facts, views, or plans, especially one for release to the media. A formal account of events given by a witness, defendant, or other party to the police or in a court of law. In this section, I am interested in statements in the sense, somewhat crudely expressed by this definition, in my opinion, of a definite or clear expression of something in speech or writing. The study of winning arguments is mostly a study of statements and the relationships between statements. Therefore, we should take care to develop a good understanding of statements. Logicians frequently provide various definitions of the word statement. In this text, I shall use the following definition of the word statement. A statement is a sentence or sequence of sentences which can be believed or disbelieved. This definition picks out a certain wide class of sentences, spanning across all natural languages and many formal languages. This class probably agrees in essential intent, if not in actual extension, with most modern logicians' definition of statement. Here are some examples of statements. I am cold. This is a pen. It has red ink. It is early in the morning. After we harvest the wheat, we will store it in the silos. Within the lives of others, we can find some of the most important insights about ourselves. Every statement is either true or false. If the axioms of math can prove themselves to be incapable of proving any statement about numbers to be both true and false, then the axioms of math can prove any statement about numbers. 2 plus 2 equals 4. 2 plus 2 equals 5. Here are some examples of sentences that are not statements. Why am I cold? Get over here. Fuck you. Help. Why am I cold is a question. Get over here and help are imperative sentences. An imperative sentence is a type of sentence that gives advice or instructions, or that expresses a request or a command. Fuck you can be literally interpreted as an imperative sentence telling the target to fuck themselves. However, fuck you is perhaps better thought of as an ejaculation. Clearly, none of these sentences can be believed or disbelieved. For example, I make no sense if I say, I believe that why am I cold, or I believe that fuck you. since they can't be believed or disbelieved. Why am I cold and fuck you are not statements. Similarly with help. Statements follow rules of grammar. Rules of grammar vary between languages, but there are various common themes. The full complexity of grammar is manifest in the grammar of statements. The grammar of statements, which is the study of grammar minus the grammar of non-statement utterances, is an interesting study in its own right. In addition, an understanding of the grammar of statements is important background knowledge for what follows. Therefore, our next step in understanding statements is to embark on a study of the grammar of statements. There are many approaches to the study of grammar. Indeed, there are a number of different kinds of grammatical theory of note. A natural language grammar attempts to describe the grammar of a natural language, English, German, etc. A descriptive natural language grammar attempts to describe the rules of grammar actually followed in ordinary cases by some population of language speakers. A prescriptive natural language grammar defines the rules of grammar that some population of speakers should use, at least according to the authors of the grammar. A formal grammar exactly describes the grammar of an artificial language, a so-called formal language. Formal grammars are usually written in notation with precise formal meaning, which renders it entirely unambiguous what does and does not constitute valid syntax for a statement of the formal language. A theory of grammar is a theory which says something about grammars as a whole, or about some restricted class of grammars. For instance, if one wishes to explain the concept of formal grammars in a thorough way, then this requires a theory of formal grammars. The Chomsky hierarchy is an example of a precise theory of formal grammars, explaining what a formal grammar is and categorizing them according to how computationally difficult it is to parse statements in them. There is a lot of interesting stuff to explore here, and I only have space to scratch the surface. Let's start by learning a simple formal language of statements. I'm going to explain how to write statements in a toy language whose only sentences are statements. This language is called first-order logic, or the language of first-order logic sometimes. First-order logic is notable in that it has an extremely simple grammar, and essentially any statement can be expressed in first-order logic. This presentation of first-order logic is notationally different from most other presentations of first-order logic, in that I opted to use English words in place of logical symbols, making the notation more naturally readable for English speakers, but less compact. In essence, the version of first-order logic I present should be equivalent to all other presentations of first-order logic, despite interesting differences. The reader can, as an exercise, find another presentation of first-order logic, and find for themselves the reasons why that system is for all intents and purposes interchangeable with ours, despite their differences. This presentation differs in tricky ways, as well as simple ways, from most presentations of first-order logic, so that this can be an interesting exercise for a student of mathematical logic. Here are some examples of statements in this version of first-order logic. A is a dog. A is a dog and A runs. For all A, if A is Santa Claus, then A is a North Pole inhabitant. For all A, if A is a person, then for some B, B is a person and B loves A. And so those are some examples of statements in first-order logic. And you should note in this audio version that I didn't read out all of the parentheses in those statements, so you're missing some details here. And really, technically speaking, first-order logic is a written language, not a spoken language. At any rate, it's not very convenient to fully communicate in speech. So as you can see, or in this case here, these statements look a lot like statements in English, but not quite. Let's go through the rules that define the grammar of this language. There are the following kinds of words in this presentation of first-order logic: variable names, object literals, predicates, copulas, such as verbs, and connective words. For variable names, I will use single italicized lowercase letters, A, B, C, etc. For object literals, I will use English phrases denoting objects, e.g., the President of the United States, or this chicken. The latter example illustrates that English phrases denoting objects can be context-sensitive in meaning. For predicates, I will use uppercase letters, P, Q, R, etc., and ordinary English phrases denoting categories of objects, specific objects, or properties, e.g., a dog, the President of the United States, clean. For copulas, I will use ordinary English copulas, e.g., loves, instantiates, and kills, as well as uppercase letters, C, D, E, etc. And so a copula is like a word that connects two object literals, whereas a predicate is a word that can be that you can predicate of an object literal. So the following are the connective words: if, then, and, or, not, for, all, some, and is. An object term of this presentation of first-order logic is a variable name or an object literal. In other words, an object term is any piece of syntax that can denote an object. We will also need notations for variables ranging over different types of words. We're going to have object metavariables, which are variables that denote some term that denotes an object, right? Or that just object term. So that's an object metavariable. And then we'll have predicate variables. Those are variables denoting predicates. Statement variables, right? Variable denoting some arbitrary statement. And then we'll need variables that range over all possible copulas. And so in the text, there are given notations for all these things, but it won't make sense in the audio. So I'm going to read that. So I'm going to not read that part, and moving forward, like, you're not going to be able to fully tell like the distinction between, like, well, what's a predicate variable, right? What's an object metavariable, right? Or, like, what's a predicate and what's a predicate variable, right? You can tell the difference between like an object variable and a predicate variable from context, but and I guess from understanding like the math that I'm about to lay out, right? You can also tell like the difference between a predicate variable and a predicate, right? But just from the reading, you won't be able to tell that. And in the text, you could tell by like whether it's bold or not. Anyway, moving forward. So a lexical unit of this presentation of first-order logic is a word, a parenthesis, or a comma. A statement of this presentation of first-order logic is any sequence of lexical units which can be formed according to the following rules. 1. If A is an object term and P is a predicate, then A is P is a statement. 2. If A is an object term and V is an English copula, such as a verb, then A, V is a statement. 3. If A and B are object terms and V is a copula, then A, V, B is a statement. 4. If A is a statement, then not A is a statement. 5. If A is a statement and B is a statement, then if A then B is a statement, A and B is a statement, A or B is a statement. 6. If A is a statement and B is a variable name, then for all B, A is a statement, and for some B, A is a statement. So, time to show how these grammar rules can be used to derive the examples I gave above of statements. A is a dog is a statement. Proof. A is a variable name. A dog is a predicate, denoting a category. By Rule 1, A is a dog is a statement. A is a dog and A runs is a statement. Proof. A is a variable name. Runs is a verb and therefore a copula. By Rule 2, A runs is a statement. A is a dog is a statement. See previous proof. So by Rule 6, A is a dog and A runs is a statement. For all A, if A is Santa Claus, then A is a North Pole inhabitant is a statement. Proof. A is a variable name. Santa Claus is a predicate denoting an object. So by Rule 1, A is Santa Claus is a statement. A North Pole inhabitant is a predicate denoting a property. So by Rule 1, A is a North Pole inhabitant is a statement. And by Rule 6, if A is Santa Claus, then A is a North Pole inhabitant is a statement. And so then by Rule 7, for all A, if A is Santa Claus, then A is a North Pole inhabitant is a statement. So that, I realize that presentation may not have been fully explanatory. This stuff can take some time to wrap one's mind around if one's not already familiar with it. So the reader should understand the foregoing to the extent that they can produce an unlimited number of statements in first-order logic, produce for each of them derivations conforming to the pattern I have demonstrated, and distinguish between valid and invalid syntax for statements of first-order logic. And so that, probably you would need to do exercises to get to that point if you haven't done this kind of thing before. I don't have such exercises yet. They are planned, so bear with me. And there are other resources that you can look into to learn first-order logic. I wish I could, recommend a good one off the top of my head, but I'm honestly not sure what I would point you to. So the reader should also understand what statements in first-order logic mean. For the most part, this may be fairly self-evident, but it's worth taking a moment to clarify explicitly what each form of statement means. A is P means that whatever object the object term A denotes in the current context satisfies the predicate P, or in other words has the property P, belongs to the category of objects P, or in some cases is the object P. AV and AVB, where V is an English copula such as a verb and A and B are object terms, means that the corresponding English statement is true for whatever objects the object terms A and B denote in the current context, right? So for example, if the statement is X runs, and in the current context X denotes Fred, and Fred is running, then X runs would be true, because the corresponding English statement, Fred runs, is true. Okay, so A and B means that A and B are both true. A or B means that at least one of A or B and possibly both, are true. The or in first-order logic is therefore an inclusive or. This can be distinguished from an exclusive or, which differs from an inclusive or, in that an exclusive or is false when both disjuncts are true. That is, an exclusive or requires exactly one of its disjuncts to be true, as opposed to at least one with inclusive or. So not A means that A is not true, or that A is false, depending who you ask. Whether not true and false are different properties also depends who you ask. If A then B means that in any case, in any event where A is true, B is also true. For all B, A means that in any variant on the current context created by setting the object denoted by the variable A to some object, A is true. For some B, A means that in at least one variant on the current context created by setting the object denoted by the variable B to some object, the statement A is true. So many connective words and phrases have conventional names. And is called conjunction. A statement of the form A and B can be called a conjunction. Or is called disjunction. A statement of the form A or B can be called a disjunction. Not is called negation. A statement of the form not A can be called a negation. If then is called the conditional. A statement of the form if A then B can be called a conditional. For all is called the universal quantifier and is one of two examples of a quantifier in first-order logic. A statement of the form for all B, A can be called a universally quantified statement or a universal statement. For some is called the existential quantifier and is one of the two examples of a quantifier in first-order logic. A statement of the form for some B, A can be called an existentially quantified statement or an existential statement. An occurrence of a variable name in a statement is called a bound occurrence if it is enclosed by a quantifier over the same variable. Otherwise, it is called a free occurrence. For example, in the statement, for some x, x is a prairie dog. The occurrence of x in x is a prairie dog is a bound occurrence, and we can say it's bound by that for some x quantifier directly surrounding it. So then, for another example, in the statement, x is a prairie dog, and for some y, x loves y. The two occurrences of x are free, whereas the occurrence of y in x loves y is bound by the for some y quantifier. But there's no quantifier over x anywhere in this statement, so x is free everywhere it occurs. So the explanations I gave of the meanings of statements in first-order logic assumed the notion of a context. For the purposes of first-order logic, the context simply determines what objects the variables and the object terms with context-sensitive meanings, e.g. it, denote. You can think of a context as a mapping from variable names to objects, from predicates to sets of objects, and from copulas to sets of objects and pairs of objects. And I'll provide a more detailed version of this conception in the section titled Model Theory, which is a subsection of the section titled Logic. So contexts are referred to by various names in the study of logic, with interpretation being one term in use. In some presentations of first-order logic, every variable name is required to be given a value by a context, while in other presentations, a context might give values only to some variables. In the latter approach, statements containing free occurrences of variables will be uninterpretable in a given context if that context does not assign values to those variables. So we'll take the latter approach in this text, and what that means is we will consider a context to provide a partial mapping from object terms to objects, saying for some subset of the set of all context-sensitive object terms, i.e. variables and context-sensitive object literals, what objects they denote. Right, so in short, a context gives values to some variables, but not to all variables necessarily. And in general, not to all object terms necessarily, but potentially to any object term. Okay, so in this approach, the one we're taking, statements containing free occurrences of variables whose denotations are not defined by a given context, and statements containing context-sensitive object literals whose denotations are not defined by that context will be uninterpretable in that context. So in short, right, if you've got an object term that refers to something, you've got an object term whose meaning is not defined by the context in your statement, then your statement is uninterpretable in that context. With the exception of bound occurrences of variables, right? If you've got a quantifier over a variable, then the context doesn't need to explain the meaning of that variable, right? That's because the quantifier helps you. Okay. So the approach of requiring contexts to define the denotations of all object terms is mathematically convenient because it entails that every statement is interpretable in every context, which is, an assumption that makes proofs much cleaner and nicer, for example. However, the assumption that every term is defined in every context is unrealistic. In reality, statements are uninterpretable when they contain context-sensitive object terms whose denotations are not clarified by the context. So I will not attempt to further formalize this explanation of the meaning of the statements of first-order logic at this time. At this point, it's hoped that the reader understands the meaning of statements of first-order logic in an informal way, which enables them to read such statements and to be able to notice the logical structure of English sentences and analyze them easily in that way. That's not necessarily hoped at this point, but that would be hoped eventually. And, of course, maybe the reader already has that competency. There are many intricacies to explore regarding the meanings of statements of first-order logic, but I will defer that discussion for later sections. Earlier, I made the claim that essentially any statement can be expressed in first-order logic. Let's now explore this claim. The claim is interesting because if it's true, then we can think of first-order logic as a sort of a theory of statements, an idealized way of thinking about statements as a whole. First-order logic is not the only formal language about which one may fairly make this claim. There are many formal languages about which one may fairly make this claim. Most of them bear some resemblance to first-order logic. First-order logic is a good example of the category. The first-order logic statements we have seen, when read aloud, are in essence English sentences, although their use of variable names is not ordinary English. Clearly, many English statements are already in essence statements of first-order logic, in the sense that a translation is obvious and closely resembles the original statement. In other cases, varying degrees of rephrasing are required to express an English statement in first-order logic. So in order to investigate further, let's abandon contrived examples and look at real sentences from out in the wild. Let's look at some semi-randomly chosen statements from books that are in my home and try to translate them into first-order logic. I don't claim that my translations are the only possible translations into first-order logic of these English statements, and I don't claim that they are exact translations capturing every shading of meaning that the statements have for every English speaker. I do claim that they are basically good translations that preserve the core meaning of the original statements. This cake is well named, as it has a very delicate consistency. Translation. This cake is well named, and this cake is very delicate in consistency, and the statement this cake is well named is justified by the statement this cake is very delicate in consistency. Sentence from The Joy of Cooking by Irma Rombauer, published by Simon & Schuster. This cake is well named as it has a very delicate consistency. Seems to mean roughly, this cake is well named because it has a very delicate consistency. That is, the sentence expresses three things. The cake is well named, the cake has a very delicate consistency, the cake is well named because it has a very delicate consistency. The third statement is expressing a relationship between the first two statements, namely, that this cake has a very delicate consistency justifies this cake is well named. This is reflected in the translation, where the copula is justified by relates the two object literals, the statement this cake is well named, and the statement this cake is delicate in consistency. Okay, next example. Every passerby could read the sign, for every passerby could read Hebrew, Latin, or Greek, the three great languages of the ancient world. So this sentence is from He Chose the Nails by Max Lucado, published by Thomas Nelson. Here's a translation into first-order logic. Latin is a great language of the ancient world, and Hebrew is a great language of the ancient world, and Greek is a great language of the ancient world, and, for all x, if x is a great language of the ancient world, then x is Greek, or x is Latin, or x is Hebrew, and, for all x, if x is a person and x is passing by the sign, then x can read a great language of the ancient world, and x can read the sign, and the statement x can read a great language of the ancient world justifies the statement x can read the sign. The size of this translation shows that many different logical propositions are contained in this not exceptionally long English sentence. So it'd be nice to sort of break down how I produced this. I don't quite understand it myself, but well enough to explain it. But I mean, I also feel though the reader should be able to do exercises like this, and hopefully when I write the exercises, that theory can be validated. So the hawk-eyed reader may notice that I've taken some liberties with parentheses. No, you wouldn't have noticed that in this reading. I'm going to skip over this discussion of parentheses. Okay, so next sentence. Besides the theories on the unity of the concept of being and the writings of Henry of Ghent and John Duns Scotus, there were other late medieval attempts to resolve this basic issue of metaphysics. Okay, translation. For some A and for some B, Henry of Ghent wrote A, and John Duns Scotus wrote B, and A is a theory of the unity of the concept of being, and B is a theory of the unity of the concept of being, and A is late medieval, and B is late medieval, and the theory of the unity of the concept of being is a basic issue of metaphysics, and for some C, not C is A, and not C is B, and C is a theory of the unity of the concept of being, and C is late medieval. Right, so in short, right, so you've got A, B, and C, right? A is, Henry of Ghent's theory, B is John Duns Scotus's theory, and then we're saying, in addition to these two, there's some C, which is not either of them, which is another thing of the same type. So this sentence is from the Columbia History of Western Philosophy, edited by Richard H. Popkin, published by Columbia University Press. Okay, next sentence. I myself in your situation, if I had an appointment with a Godin, Godette, Godot, anyhow, you see who I mean. I'd wait till it was black night before I gave up. Here's a translation. If I have an appointment with Godot, then, if not I am waiting for Godot, then the time of day is black night. Okay, so that is a funny sentence from Waiting for Godot by Samuel Beckett, published by Grove Press. And this translation omits the difficulty the speaker has in referring to Godot and simply refers to the individual the speaker is referring to, namely Godot. So if we wanted to translate the difficulty literally into first-order logic, we could write something like, for all x, if x is Godin, or x is Godette, or x is Godot, then you know the referent of x, and if I have an appointment with x, then if not I am waiting for x, then the time of day is black night. This example illustrates that there can be multiple plausible translations of an English statement into first-order logic. This is a usual feature of translation from any language into any other language. So in order to ensure their understanding of the foregoing, which is necessary for understanding of what follows, the reader should ensure they are able to translate statements from English into first-order logic. Perhaps it is evident to the reader how to do this from what has been said. The reader is encouraged to find English statements and translate them into first-order logic. Especially if this exercise is difficult, the reader can try the provided exercises, yet to be written, which include answers and walk through the process of arriving at those answers. Promises. Okay, the reader is encouraged to try to find limits to what first-order logic can express. The reader is encouraged not to conclude that first-order logic can't express something just because the reader can't quickly figure out how to express it. Philosophy.stackexchange.com is one place to ask questions and find answers to already answered questions about this kind of topic. Questions like, how can this statement be translated into first-order logic? Some statements may lack any wholly satisfactory translation into first-order logic. We will explore this topic in more detail later. So to-dos, a couple to-do items here. Discuss general techniques for eliminating English grammar constructs not present in first-order logic. And another to-do, discuss philosophy of translation into first-order logic in more depth, including the limitations of translation. So, bit of construction going on in this part of the text. So let's step back and consider what we've learned so far. We set out to study the grammar of statements. We studied the grammar of statements in a version of first-order logic. We also developed a practical understanding of how to translate English statements into first-order logic. Thus, we have seen that although the grammar of English statements is very complex, for many practical purposes we can reduce the study of English statements to the study of statements in a much simpler and more precisely defined language, the language of first-order logic. This is because for essentially every English statement, we can find a statement of first-order logic, which means essentially the same thing. Almost every lesson that we learn about first-order logic will translate over to English fairly straightforwardly, but first-order logic is much more amenable to rigorous study than English is, because numerous distracting sources of non-essential complexity have been eliminated in first-order logic. Therefore, the introduction of first-order logic can be expected to substantially simplify our lives in the study of statements, and allow us to get further along in understanding them. However, it would be wrong of us to carry out our study of statements only in first-order logic indefinitely. Ultimately, everything we learn must be applied to English statements. Arguments are always made in natural languages, almost always, of which English is the example used in this text. Working in English must not be a handicap for us. As debaters, we benefit from wishing to become such masters of the full complexity of the natural languages we use that the complexity is something we turn to our advantage, rather than something that stymies us. However, practically speaking, mastery of English insofar as English differs from first-order logic, is more a matter of acquaintance and art than it is of theory and technique. Mastery of first-order logic, on the other hand, is mostly a matter of theory and technique. Acquaintance and art come only from practice, and in this book our focus outside of the exercises is on theory and technique. This simply means that the reader will mostly have to figure out for themselves how to apply the theory and technique of logic to natural language arguments. The reader should seek to synthesize for themselves a deep intuitive understanding of the theory and technique of logic, and allow it to sink into their mind until it underpins their thinking even on an unconscious level, if they haven't already done that, of course. This, in my experience, is what enables the reflexive, sophisticated application of logic to natural language. And the exercises that I have promised should help with that. Hopefully I am able to keep that commitment. Hopefully I'm not hit by a bus or anything before I get around to it. Yeah, that's all I've got.